All right, so here we're going to take a look at a couple of subspace constructions of sets that we've looked at before. All right, so the first one we're going to look at is the null space of a matrix. So the null space of a matrix is a subspace. All right, so if we remember that for any M by N matrix, the null space is a subspace of R to the N. All right. Okay, so now let's prove why that is true. Okay, so first let's show that it's not empty, right? The null space always includes the zero vector. All right. Again, because here, if we think of the linear system, the homogeneous system here, and this is always true, right? Zero vector is always a solution, right? Okay, so check here, not empty. All right, so now let's check the other two. Closure under vector addition. So for part B, our second one, so remember that if ax is equal to 0 and ay is equal to, the zero vector. All right, so in other words, y is an element of the null space of A. All right, so if that's true, let's take a look at the sum x plus y. All right, so this, again, using properties of matrices, I can distribute along here, and each of those are the zero vector, which equals to the zero vector. So that way we know here that it is closed under vector addition. So the third one is it closed under scalar multiplication. So again, if ax is equal to 0, right, and alpha is a real number, right? So now let's take a look at this. All right, and for here we can, since this is a scalar, we can use properties here of scalars and rewrite this like this. Right? And then this is a times x is equal to the zero vector by assumption, and then multiplying the zero vector by a scalar, right, vector space properties, gives me back the zero vector. All right, so what this says, that the null space is not just a solution set of a homogeneous system, but it itself is a vector space. So the null space of any matrix A is a vector space. All right, so it will satisfy all those 10 axioms there. Okay. So now the next example we're going to take a look at is just in general, the span of a set is a subspace. All right, so here's what I want to prove here. So for this example, we have for any vector space V, and any subset S subset of V, the span S is a subspace of B. Okay. All right, so again, here for our proof here, let's set S is just a set of vectors here, U1, U2, U sub n. All right, just some subset of a vector space. All right, and I want to prove here that the span of S is a subspace. So first let's show that it's not empty. Well, I can remember, what does it mean to be an element of the span? So here it means that you are some linear it means that this here is an element of the span of S, right? Just a linear combination. Now, if I can choose those scalars to all be 0, so now we have 0 times U plus 0 times U2 plus 0 times UN. And we get the 0 vector, right? All of these are 0 plus the 0 vector plus the 0 vector. So it's not empty, right? Okay. All right. So it includes the 0 vector. So 0 vector is an element of the span. Now let's show that it's closed, and this is actually a proof we have done in this class before. Let's show it's closed under vector addition. So let X be an element of the span of S, and Y be an element of the span of S. All right, so that means X can be written as some linear combination of the vectors in the set S. And then Y, let's say beta 1, beta n UN. And we look at the sum. And again, rearranging the terms and factoring out the vector. Here we have just another linear combination of the vectors in S. So what that tells me is that X plus Y is an element of the span of S. Hence it is closed under vector addition. And in the same way, right, we could say, all right, let alpha be element, just some real number, right? And then X is, as before, element of the span. And then alpha times X is alpha times alpha 1. Actually, let's choose just to avoid confusion here, let's choose a constant C. Alpha 1 U1 C alpha n UN. All right, and then just distributing, we get C alpha 1 U1 plus C alpha n UN. Okay, and then here we see this is just again another linear combination of the vectors in S. So Cx is also an element in the span of S. So now here, the span of S is a subspace of V, or just a vector space in general. Okay. All right. Now, one important thing to notice here about this proof here is that I did not make any mention of column vectors, R to the n, right? This was all done in very general terms of a vector space. And this idea of a linear combination and a span still held, right? It held because a vector space is it's defined rigorously in terms of addition of vectors and multiplication by scalars. Okay, so we can continue using these definitions for linear combinations and spans, not simply for our Euclidean space, for just for any vector space in general. And that's what we will be doing moving forward.